Okay, those things are out of the way. Today we're going to be looking at Newton's law problems. We'll be doing many of the same things we've done before with free body diagrams and vector versions of the forces acting and things like that. But today we're moving on to circular motion. And so we'll be needing a centripetal force to produce a centripetal acceleration. And we're looking at how those arise today. So we'll start off with a one plane problem, actually one airplane problem, one model plane problem, and then go on to some driving or road problems. First, we have a plane flying in a vertical inside loop. And inside loop is one where the pilot's head is toward the center of the loop. There's such a thing as an outside loop, which I guess is much more exciting to perform, where the pilot's head is continually pointing away from that. But an inside loop, anyway, of radius 3.00 times 10 to the third meters. So basically a 3-kilometer radius of curvature. At the very top of the loop, the speed of the plane is 211 meters per second. What's the normal force exerted by the plane on the pilot? So I'm going to have to draw a picture for this thing, kind of. Nothing very fancy. Let's see. I'll mark the center of the circle. Just draw a circle here. And this will not be to scale, but up here, we'll have this airplane that, kind of looks like this. It'd have a wing and of some sort and a propeller assumed. Anyway, but for the pilot in this case, I'm just going to imagine this is a pretty strange looking airplane seat. Anyway, there's the pilot. Their hands are on the whatever it is that the pilot's hands go on to. And so anyway, there's the pilot. And at the bottom, the situation here would just be flipped upside down. So we can dispense with the airplane at the bottom, I guess, and just there's the seat that the pilot sits in, and they've got their hands on the, I don't know what, the part of the airplane that the pilot puts their hands on while they're flying. Anyway, so that's the situation. So let's go to the top here and make a free body diagram. That's, we've got a sketch. Next step in a Newton's law problem is to make a free body diagram. Forces acting on the pilot. Well, there'll be mg acting downward, and there will be the normal force of the seat on the pilot also acting downward. By the way, when you're sitting in a chair, you can feel the contact force between you and the chair. That's the force that the chair is exerting upward on you. You are simultaneously exerting a downward force on the chair. That's the third law partner of the normal for the chair, but that's what we'll have. Okay, well, let's just let downward be positive for this part A here and see what we get. So that's the positive direction. Since it's really just a one-dimensional problem up here at the top, let's just say that down is positive and N plus mg, this is the old sum of the forces equals ma. N plus mg will equal ma. Okay, the acceleration of the airplane. Well, in this case, we have another equation we can add into here, and that is that the acceleration is going to be centripetal acceleration. So it'll be v squared over r, and we can calculate a number for that. Well, let's figure out what the normal force is going to be. This would be it sounds weird, but the perceived weight of the pilot at this time is actually going to be downward. Whoops. Yeah, MA minus MG. That's right. So let's see. I guess we could factor out. Let's just go ahead and calculate the centripetal acceleration here. It's going to be V squared is 211 meters per second. And we have to square that, divided by 3.00 times 10 to the third meters. Unit-wise, meters squared per second squared divided by meters will give us meters per second squared. And that's what we want for acceleration. And I get about 14.8 meters per second squared. Okay, and then the normal force is going to be, I'm going to factor out the M here, and it's 48.0 kilograms for the pilot's mass. If I factor out the M, it's going to be A minus G left inside the parentheses. And as far as sig figs, if I write this as 9.81, I'll end up losing that 1 there, and I'll just have the normal force will be 48.0 kilograms times 14.8 minus 9.8 is just going to be 5.0 meters per second squared. And so 5 times 40, that's 240 newtons. Yeah, and we're down to 2 significant figures here. Now this compares to the pilot's weight. The pilot's weight is going to be the mass times the acceleration due to gravity. And I don't feel like doing that one in my head, but it's actually about 400. I can keep 3 sig figs on that. It's 471 newtons. So the normal force between the pilot and the seat is going to be about half of their regular weight. So they'll have a perception of weight, but it's in the direction opposite normal, and it'll only be half of its usual value. But that normal force is plus the weight is actually what lets the pilot have the centripetal acceleration. Okay, well, what about part B? What's that going to look like? I think I can just kind of slide this over here. For part B, and by the way, you can print off this file, but the plane speed has doubled. So the speed for part B is, instead of 211, it's going to be 422 meters per second. If I do a free body diagram for the pilot at the bottom, we'll have mg downward, and the normal force is upward here. And so if I say I'm going to let upward be positive for this part, that's the direction of the acceleration. So I'll just let that work to my advantage here. And with positive being upward, the sum of the forces equals ma. I'll have n minus mg is going to equal ma. And the weight is working against the normal force in this case. They still have to have their centripetal acceleration produced by these two forces, but it means in this case that the normal force has to overcome the weight, and then it doesn't have the weight helping it out on here. So we'll have that the normal force is going to have to be magnitude of MA plus the magnitude of the weight. So we'll have M times A plus G this time instead of A minus G. Acceleration is going to be a lot more in this case. We'll have V squared over R again, 422 meters per second squared over, it's still 3.00 times 10 to the third meters for the circle that they're traveling, but this is going to be a larger acceleration. So I get, let's see, 59.4 meters per second squared. Okay, that's a fair amount. Okay, well, our normal force in this case, we'll see how it compares to the pilot's regular weight. It's going to be the mass, 48.0 kilograms, times that acceleration, 59.4 meters per second squared, plus 9.81 meters per second squared. And again, we're going to lose that one because we've only got precision to the nearest tenth here. And I get about 3,300 and yeah, I can keep three significant figures here. So newtons, which if I divide that by the pilot's weight, okay, this is about 7 times the pilot's weight. And so they're going to feel, every part of them is going to feel 7 times as heavy, including their arms. It'll be hard to hold their arms up at the bottom of that loop. So kind of challenging. Okay, any questions on that one? That was kind of a gentle introduction. We were able to get away with some stuff. That one, it wasn't too bad. Now I want to do one that is a little more complicated. We have a model airplane of mass 0.75 kilograms, not much. This is one of the kind of old style model airplanes that flies at the end of a control wire. Nowadays, it doesn't cost much to get one that has a little remote control and stuff like that. But anyway, 59 meter control wire, a speed of 35 meters per second, and compute the tension in the wire if it makes a constant angle of 20 degrees with the horizontal. And they give us a free body diagram here. So the forces exerted on the airplane are the pull of the control wire. That'd be the tension here, which is going down to presumably the owner of the airplane. And they'll have their hands on some kind of a thing that they're holding on the control wire there. Let's see, the weight of the airplane, and there's aerodynamic lift. And the plane's going to be flying at a tilt kind of. So this T line is sort of the plane of the airplane's wings, I guess. And the lift is perpendicular to the way those wings happen to be aligned. So those are the forces that are acting here. Now, Here's something that is different about problems like this, and we'll see this when we get to bank turn examples here pretty soon. But the direction of the acceleration here, what is the circle that the plane is flying in? It's going to stay whatever height it is above the ground. It's going to stay at that height. And the circle it's traveling in is going to have its center over here in this direction somewhere. And also the radius of the path that it's traveling is not going to be 59 meters. It's going to be whatever this distance happens to be. This is 59 meters here, and I know this is not to any sort of scale, but that's the 59 meters. The radius of the path that it's traveling in is in that direction. Now, the acceleration never belongs on the free body diagram, but it's okay to sketch it in off to the side. And in this case, I'll just do this. That's the direction of the acceleration there. These things are boldface, which in old physics textbooks, that's how they indicated vectors, but that's what we'll have. And we can write Newton's second law here in vector form. It's going to be that F lift, I guess. Boy, that's tiny print on that, and it's even hard to read from this far away, plus the tension, plus mg is going to equal ma. That's the sum of the forces equals mass times acceleration. Okay. I think before I get too far along here, I'm going to calculate that radius that it's actually traveling along. And I've got 59 meters here. I've got a 20-degree angle here. It says 20.0. So, although all the other numbers are only to 2 sig figs, so, but we can use this anyway. We'll just keep 2 sig figs. And let's see, this will be a right angle over here. So this side is the one adjacent to the 20-degree angle. So this side divided by 59 meters will equal the cosine of 20, or this will equal 59 meters cosine of 20.0 degrees. So the radius of the circle, if the airplane is actually traveling, is going to be it helps to turn the calculator on first. Okay, I get about 55 meters for that. So it's not the entire length of the chord there for the radius. Okay, we know it's speed 35 meters per second. In this case, we also know that it's traveling in a circle, so its acceleration is going to be centripetal. That'll be v squared over r, which 35 meters per second squared divided by those 55 meters. We can just get a little bit of a feel for what's going on here. And I get about, not a huge acceleration, 22 meters per second squared. Okay, well, that's a little bit of preliminary work. We had to have these numbers for solving this thing, but let's select a coordinate system. Okay, how do we do this? What is it that we're after? Compute the tension in the wire. Okay, that's the thing that we're after. Let's see, do we know that aerodynamic lift force? We don't. However, let's see what we can do here. On a problem like this, one possible thing to do would be to have a tilted coordinate system, and we could do it that way. We could have X pointing down toward the person in the direction of the tension, and we could have Y pointing in the same direction as that lift force. And then we'd have to figure out components for the weight, which isn't bad. And we'd have to figure out components for the acceleration as well. If we go with the usual coordinate system, which would have X pointing in that direction and Y pointing vertically upward, we won't have to compute components for the weight or the acceleration, but we would have to calculate them for the tension and the lift force. So this is a problem where it's actually a toss-up, which coordinate system you use. I think I'll pick one of these and solve it that way. And for extra practice, you could try picking the other one and solving it for the other one. And I think I'm going to go with the tilted one, just because it's the tension that I'm after and I won't have to mess around with components of it. So let's write down our forces in terms of a tilted coordinate system. The tension's going to be easy. It's just going to be whatever its magnitude is in the I hat direction, because I chose my I hat to point down this direction. Also the lift force, which I don't care about. I could figure it out when I'm done, but that one is going to point in my Y direction, so it'll be whatever its magnitude is times J hat. So there's that one. Now mg, it's going to have this is also a 20-degree angle down here. And I'll draw a little triangle to calculate it. This is that 20.0 degree angle. This part down here, oh, these two are perpendicular. mg, or this component divided by mg, is going to be the sine of 20 degrees because mg is the hypotenuse. So this will be mg sine of 20.0 degrees. And this part here is adjacent to that 20-degree angle. So this would be mg cosine of 20.0 degrees. And actually, I can plug in the numbers later, but for now, I can just write mg is going to equal mg, G is the one that's the thing, but I'll have mg sine of 20, and that'll point in the positive x direction. So in the I hat direction, and the mg cosine 20 is in the negative y direction, so minus mg cosine of 20.0 degrees in the j hat direction. And we get, it's a switch from our usual components. The I hat gets the sine and the j hat gets the cosine because that angle is measured with respect to something, well, the y axis actually in this case. So that's why that's different. Okay, the only thing left is the acceleration. Acceleration, if I draw a picture for it, well, actually just the acceleration, but let's go ahead and hang on to the MA. Remember that we've got X pointing in this direction and Y pointing in that direction. So if I convert this into an X component and a Y component, this is our 20.0 degrees again, showing up everywhere. The X component of MA is going to be the cosine term. So MA as a vector will have MA cosine of 20.0 degrees in the I hat direction. And it'll have a y or j hat component that points that way. That's going to be positive also. So plus MA sine of 20.0 degrees in the j hat direction. So those are my forces. Okay, well, it's the tension that we're actually after. So let's just concentrate on the I hat terms and kind of do a little thing here. I hat terms. Just there's my Newton's second law in vector form. If I take out the I hat terms from each one of these, well, the lift force doesn't have one. T does. It's just going to be T. And I'll also have mg's got an I hat term. So I'll have T plus, and it's also positive, mg sine of 20.0 degrees. That's it for these forces. On the right side of the equation, I've just got ma cosine 20.0 degrees. So that will equal ma cosine of 20.0 degrees. So that's the scalar equation that I have to solve. I know the mass. I calculated the acceleration. G is just our usual 9.81. And so I know I can figure out this and I can figure out this. And all I wanted was the tension in the cord. So I'll be good to go. T will equal, I guess I could factor an M out of this thing. So M times A cosine of 20.0 degrees minus G sine of 20.0 degrees. Okay, because that component of the weight is helping to produce the centripetal acceleration in a weird sort of way. It's contributing to the tension. Actually, it's not helping with the acceleration because it's perpendicular to it, but it does reduce the tension that's needed. So I will have whatever the mass, 0.75 kilograms. And now it's just plugging numbers in. The acceleration we figured out, 22 meters per second squared, cosine of 20.0 degrees minus 9.81 meters per second squared, although I don't think we're going to get to keep all these sig figs. Sine of 20.0 degrees. All right, kind of messy. Yeah, we're only going to get to keep 2 sig figs, but 22. And I forgot to turn on the calculator again, as usual. I wish this would stay on longer. I might be able to program it to do that. And not much. I get about 13 newtons is all I get on that thing. So not a whole lot. But this one, it had a tilted coordinate system, but the really new thing here was having to make note of the fact that the acceleration wasn't in the direction of this tension. It was toward the center of the circle. So when you're looking at these circular motion problems, think hard about where the actual center of the circular path it's on happens to be. And something that we'll have to consider, especially on these banked curve problems. So here we have a civil engineer wishes to design a curved exit ramp for a highway in such a way that a car will not have to rely on friction to round the curve without skidding. In other words, a car moving at the designated speed can negotiate the curve even when the road is covered with ice. I'll try to mention something about seeing what happens if the road is covered with ice and you're on a banked curve. I saw something kind of funny one time. Funny for people watching it anyway. Let's see. Such a ramp is usually banked. This means the roadway is tilted toward the inside of the curve. And suppose the designated speed for the ramp is to be 26.8 meters per second. That's 60.0 miles an hour. And the radius of the curve is 248 meters. At what angle should the curve be banked? So if we just do a sketch for this thing, I'll draw a very exaggerated angle for the banking of it and just call it this thing theta, the amount that it's banked at. And I start drawing my car by making black tires. And so that's the way the thing looks. And we're looking at the car from, I don't know, the back or the front or something like that. And so anyway, that's supposed to be a car. We're just looking at the tires there. And imagine that its velocity at this instant is into the page here. So we have something like that. Okay, well, there's a sketch. Now, as far as a free body diagram, you can just draw the forces acting on this car. It says no friction, so scary if you're driving. There's our mg, and I'll draw a horizontal line here just because mg is perpendicular to that, but then I'll draw the banking of the road. Whoops, that's even steeper than the other one I drew. Anyway, this is the angle theta, and the normal force is going to be perpendicular to the road surface, which is that I've got there. So I have that. And let's see. Okay, that's it for forces. There's no friction, so there's no sideways force here. As a reminder to myself, I'm going to draw a little arrow on here that points in the direction of the acceleration. Okay, I don't connect it to the dot because it isn't a force. It's the result of the forces, but it's parallel to this horizontal line here. And that's something that I have to have in mind. Okay, this time I've only got 3 vectors in the problem. So if I think of Newton's second law in vector form and say that the sum of the forces equals ma, well, I'm only going to have n plus mg equals ma. Hey, how many vectors do we have in that equation? Just 3. We can probably do this one pictorially if we want to. We can have a right triangle because the MA vector and the MG vector are perpendicular to each other. And let's just see what comes out of that. By the way, the magnitude of the acceleration is going to be v squared over r. So that's a number we can calculate. Let's see. I think we're going to have m's in a lot of the terms, but because we don't have the mass of the car, actually. Might have to do a little bit of monkeying here. Oh, that's not going to be too easy. Maybe I can. Let's see. Okay, let's take the N and the MG. And so I draw, I'll draw a horizontal thing and then our kind of tilt angle theta here. So here's theta. N is perpendicular to this tilted thing. normal force is always perpendicular to the surface. So there's N. mg points straight down, and it has to point straight down to a point where this plus mg is going to equal ma, and a is horizontal from that starting point. So ma is going to be right here. I think I can do it. Okay, let's see, that's 20 degrees, that's 20 degrees. This is 90 minus 20 degrees. That makes this thing our, or not 20, but our angle theta again. We're trying to get theta. And if I look at this, right angle down there, let's see, MA divided by MG, this would be the side opposite divided by the side adjacent to that 20-degree angle. It's not so easy to see on this one, but MA over MG will equal the tangent of theta, and the m's divide out. I don't have to know the mass. I was thinking I might have to do a little monkeying around to get that fixed. That means theta is just going to be the inverse tangent of A over G. Well, let's calculate the acceleration here and see what we get. 26.8 meters per second. And the radius of the curve is 248.0 meters. So that acceleration will be I can only keep 3 sig figs on this, and it actually turns out to be 2.9 meters per second squared, or 2.90 meters per second squared. So I'll have the inverse tangent of 2.90 meters per second squared over 9.81 meters per second squared. For the argument on a trig function, you'd better have your units divide out, because you can't have any units on the argument of a trig function. They have to go away to be pure ratios. So anyway. Okay, I get, let's see, only about 1.65 degrees. So, that's typical, actually. Banked curves usually aren't very steep. Anyway, my my story about a banked curve, this was a long time ago, but my wife and my brother and I were driving up to the top, or at least to the ski area on Mount Spokane one time. We were going to be cross-country skiing, and that road is pretty curvy, and it happened to have been one of those snowfalls that it's just the really wet, fluffy snow that as soon as it gets packed on a road, it's really slick. And there was quite a bit of traffic heading up there that day for people going skiing. And anyway, the traffic got stopped on a part of the road that had kind of a more than a 1.65 degree angle of slope anyway. And there was a car in the line with us, and they must not have had very good tires, because their car actually started being stopped. It actually started to slide downways in this direction. And the driver of the car tromped on the gas. which makes things worse because then your tires are spinning and you don't have static friction anymore. You've got kinetic friction, which is lower, and the car just continued to slide and slide and slide downward down into the ditch. Fortunately, there was all kinds of people around who were able to push the car out, but the guy had horrible tires, and I don't know how he was going to get up the hill. This was before it even started getting slick. So, all right. So we just calculated the angle at which the curve had to be banked. So we could be civil engineers if all of the problems looked like that. Let's try another one. Now we have the car is traveling at constant speed around a banked curve on a highway. For starters, assume the highway is extremely slick. Okay, so that the friction between the tires and the road is essentially zero. The curve is banked at 2.0 degrees, and the curve has a radius of curvature of 420 meters. Solve for the speed at which the car can safely negotiate the turn. Let's see, there's just one after this. But on the sheet that I posted that you can print off, I gave these directions to one, sketch the situation, then draw a free body diagram for the car, write Newton's second law in vector form, select and describe a coordinate system, justify your selection. Okay, sometimes those are a toss-up. We did that on the previous problem. And then express all the vectors from part C in unit vector notation. So on this problem, we won't have friction, but even though it's probably going to be a 3-vector problem, I'll go ahead and do it in unit vector notation so you can see what it'll look like. And then set up equations and solve for the speed at which the car can safely negotiate the turn without sliding. So I've been going through these steps on just about every problem I did, except for the ones that are 3-vector problems. And I could actually kind of skip D and E on those ones, but I'm going to go ahead and do it this time. So traveling at constant speed around a banked curve on a highway. All right. I don't know why. Maybe it's because I'm severely right-handed. Whenever I draw these things, I make the slope go up that way, which means an awful lot of the time I've got an X coordinate system that's pointing in that direction or that direction, but that's okay. If you don't like it, you can just imagine walking around and looking at this from the opposite direction, and then you'll have your X coordinate going to the right. So again, I've got the wheels of the car on the road, and so here's sort of the looking at the car from either behind or in front in profile. Looks like a pretty funky old car. Anyway, that's the way it's going to be. And the acceleration is going to be in this direction. So just keep that in mind. So there's my sketch. Now I'll do a free body diagram right underneath this thing. I'll have mg downward like that. When I'm making free body diagrams where I've got some tilted forces, I usually do something to indicate some directions on here. So that's supposed to be theta. And the normal force here is perpendicular to the road surface. So it's going to be that way. So this is going to be perpendicular. And then something that I like to do off to the side of these things is just put a little arrow that indicates the direction of the acceleration, or maybe a big arrow, but that's the direction of the acceleration toward the center of the curve. Next thing, write Newton's second law in vector form. Pretty easy this time. In general, it's always the sum of the forces equals ma. In this particular case, there's only 2 forces acting. So I'll have N plus mg equals ma. And let's see, I think I'm going to go with the coordinate system. If I go with a coordinate system that'll have X pointing this way and Y pointing this way, I've got three vectors in this problem. And if I have X going this way and Y going this way, I won't have to calculate components for mg because it's in the minus Y direction. I won't have to calculate components for MA because it's that way. And I will have to calculate components for N. Okay. However, that's only one vector out of three. And if I used a tilted coordinate system, I'd have to calculate components for two of the three vectors, and I'm lazy. So I'm justifying my choice of coordinate system with my laziness. It's just less work. All right, well, now I'll write my vectors in ij hat notation, and I'll do the easy ones first. MA is just going to equal whatever its magnitude is, and it's pointing in the positive X direction. So it's just MA along I hat. MG is, it's just pointing straight down. It's just going to be minus MG in the J hat direction. And for the normal force, I will have to do a little bit of work. However, it's not that bad. So I'm going to draw a normal force, a big long arrow for it, so it's not too confusing. And this is the Y direction here. Oh, let's see. It happens to be perpendicular to the road surface, which is in this direction. It's banked at a 2.0 degree angle, and I know I'm way exaggerating that 2.0 degrees, but that's okay. There's 2.0 degrees. This is a right angle right here, and so this would be 88.0 degrees. And this is also a right angle. This is up the plane. This is the slope of the road. The normal force is perpendicular to that. And that means this is another right angle, which means this is 2.0 degrees. And looking at this, I can say that this component will equal whatever the magnitude of the normal force is times the cosine of 2.0 degrees. And that's the J hat component. And then I'll also have this one divided by the hypotenuse would be the sine of 2.0 degrees. Anyway, I'll end up with this. And check my math on this, convince yourself of this, but should be MA sine of 2.0 degrees in the I hat direction plus MA cosine of 2.0 degrees in the J hat direction. So that's what I have. Now it says solve for the speed at which the car. What was I just doing? It's N that I'm talking about here. Nobody caught it. Okay. Anyway, N is going to equal N sine of 2.0 degrees in the I hat direction plus N cosine of 2.0 degrees in the J hat direction. I was thinking ahead a couple of steps and I shouldn't do that. Anyway, that's what the normal force is. So now what have I got? If I look at the sum of the forces in the X direction, that'll just equal MA. And what have I got in the X direction? Well, I've got, I have N sine of 2.0 degrees. So will equal MA. That's the force that is producing the centripetal acceleration. A little bit scary. That's not that big a force. It might be easy to slide off this road. Let's see. And then the sum of the forces in the y direction are going to equal 0. There's no acceleration in the y direction. And that's just going to be n cosine of 2.0 is equal to mg. Or no, minus g, excuse me, is equal to 0, but that will make it equal to 0. Thinking a step ahead again. All right. Well, I can figure out what the normal force is from this. It's just going to be mg. I'm doing two algebra steps at once here. Kick the mg across, divide by the cosine of 2.0. And if I take this expression for n and stick it up here, I will get mg over cosine 2.0 times the sine of 2.0 is equal to ma. And look at that. I don't need to know the mass of the car. It divides out. And I'll have sine 2 over cosine of 2. That's the tangent of 2. I'll have g tangent of 2.0 degrees is equal to the acceleration. Buried within the acceleration is the speed of the car, because this is equal to v squared over r. It's centripetal acceleration again, like all of these are. If I multiply out from underneath by r and then take the square root, I will get v is equal to the square root of r g tan of 2.0 degrees. And that will be, the radius of the curve is 420 meters. Times 9.81 meters per second squared, and the tangent of 2.0. Now let's see, that'll be meters squared per second squared under the square root, but when you take the radical, take the square root, you just get meters per second. So unit wise, we're good. We can figure out what this is. And I get 12. Let's see. I've only got two significant figures on this one I know of, and also on the angle. So I'll just call it 12. Well, it comes out almost exact anyway. 12 meters per second is the speed, which isn't very fast, but if you have zero friction, you don't want to be messing around with this. The kind of bad thing is that if you stop your car and you have essentially no frictional force on there, it could potentially slide, although there's going to be some frictional force, and it probably won't if you stop your car. But if you step out of your car, you might end up having your feet go out from underneath you. So that could happen. Well, it's 12:40. I don't know if I can get this one done. This one's maybe a little more complicated, although I may go ahead and solve it, and then it'll be in the recording, so you could come back to this thing and do it. Now we have a car traveling at constant speed around a tighter turn that's banked at 5 degrees. Radius of curvature is 285 meters, so the other one was 420. and we've got a coefficient of friction of 0.68. Solve for the speed at which the car can safely negotiate the turn without sliding. Now, this one, when we say safely negotiate the turn, we'll make the assumption that they're pushing the limit and not going slow, but they're going fast enough so that if they were to slide, they would slide up the thing. And we'll imagine that they're maxing out the static frictional force. So here's our angle 5.0 degrees. Again, I way exaggerate them, but that's okay. Here's the car, the tires anyway. And we'll have our usual thing that looks like one of those cars out of a 1940s movie or something. Or, yeah, so this is a guy, a moonshiner who's running from the revenuers or something like that. Okay, there's our sketch, free body diagram. We'll have mg downward as usual. We'll have a normal force, which is perpendicular to the road surface. So here's our 5.0 degree angle. And I think that's kind of perpendicular to it. There, now it is. And this time we'll have friction. And the friction is down the plane, which means it's keeping the car sliding up the plane of the road. Remember, this isn't really this big an angle. And keep it from sliding up this way and going off the road. So the friction is going to be down this way. So that's the frictional force. And just as a little reminder to myself here, the acceleration is in this direction. Okay. So Newton's second law. All right, in general, it's always this. You've seen me do this a million times and not really do anything with it. But just a reminder, sum of the forces equals MA. The forces in this case, we've got 3 of them. So N plus mg plus F in this case is going to equal MA. A couple of reminders to myself. The acceleration is going to be centripetal acceleration, so it's v squared over r. The frictional force is going to be mu sub s. We've got static friction, so mu sub s times the normal force. So probably to solve this thing, I'm going to have to figure out what the normal force happens to be and see where I go from there. Okay. Well, right. Select a coordinate system. What should we select in this case? I've got 2 vectors that if I have a horizontal vertical coordinate system, the acceleration and the mg, I won't have to calculate components for. I've got 2 other vectors that I will, and if I have a tilted coordinate system, I don't have to have components of those 2, but I will have to have them for these 2. But I think I'm going to go ahead and go with the horizontal vertical component system that we often use. So this will be my y direction. It's a toss-up this time, to tell the truth. So you could go either way. And it would be good practice for you to, after you see me do it this way, try rotating the coordinate system so that F is in the direction of that thing and see how it comes up. All right, components on this. Let's go ahead and start with the normal force and figure out components for it. May as well bite the bullet here. Now, the normal force is perpendicular to the road surface, which Here's this 5-degree angle. I'm going to call this theta, so I don't have to keep writing that. Anyway, here's theta. This angle here is going to be 90 minus theta, because these two are perpendicular, but this is perpendicular to that, so this is going to end up being theta again. And this is my normal force. Okay, so it looks to me like the normal force will equal n cosine theta in the I hat direction, excuse me, n sine theta in the j hat direction. So plus n cos theta in the j hat direction. And you can kind of check that. If you've got a horizontal surface, okay, so we tilt this back down, the normal force, the sine of 0 is 0, and so you won't have a normal force in the I hat direction on a flat road on a horizontal surface. Similarly, the cosine of theta is 1 on a horizontal surface, and on a horizontal surface, you'll just have a vertical component to n. So that part checks out. Okay, what's the other thing that I have to have components for? The frictional force. Okay, it's doing something very much like that, except here that angle theta is going to be measured with that. Let's see. Frictional force. I'll draw a big picture for it too, so we can get that understandable. Okay, this is the frictional force. Oh, that's not the frictional force. Excuse me. This is the frictional force. Okay. But that thing I drew first is actually its horizontal component. This is the angle theta again. So the frictional force will have a horizontal component that's going to be F cosine of theta. And it'll have a vertical part that's in the minus y direction, wherever I drew my y. Yeah, that's going to be F sine theta. Now, if we have a horizontal surface, it shouldn't have a j hat component, and it won't, because if we have a horizontal surface, theta is 0, and the sine of 0 is 0. So this part would vanish. So those check out. And what else have we got? mg. That's just in the minus y direction. My voice is going, but that's okay. We'll live with it. And MA is just going to equal whatever its magnitude is in the I hat direction. So let's look at the maybe J hat terms first. The sum of the forces in the X direction, those are, or the Y direction, excuse me, those are equal to 0 because the acceleration's in the X direction. So what have we got? We have n cosine theta let's see, minus F sine theta is equal to 0. Okay, maybe we can make some sense out of that. Is that it? No, I've also got minus mg. So I have that thing. Let's see, some of the forces in the X, that's a mess. I'll try to make that better. There, that's better. Oh, and you said and minus mg. You're right. Okay, so sum of the forces in the x direction. Those will equal ma. And in the x direction, we've got n sine theta and f cosine theta. So plus f cosine theta is equal to 0. Oh, nope, equal to ma. I was glancing up to see if there was another comment. Okay, this one's kind of complicated. But I think I can do something with maybe. Now I'm starting to wish I had used a tilted coordinate system, because that would have simplified some of this stuff, but we can just see what we might do algebra-wise on this thing. Minus f sine theta equals mg. I just took this equation and changed it. I can see something kind of messy to fix this. Foresight or hindsight is 2020. It would have been easier to do this the other way, but let's see. Well, actually, theta is just a number. We know what it happens to be. If I add these two equations together, well, I'd still have two unknowns in each one. I may stop here and think about this again, and I might just back up and go with a tilted coordinate system unless I can figure out a tidy way to do this. But it'll take me a minute to do that. If I was doing this and it was a homework assignment, I'd back up and tilt the coordinate system and not have those components on F and N. So, all right. But anyway, I'm going to stop the recording here and fix my mistake, maybe. So, stop screen sharing. I don't know what to do about this. Anyway, I'll stop the recording and oops, let's Alt R again.